All right, so good afternoon, everyone. So today we're very happy to have Dr. Jinyuan Jia here to give a talk titled Machine Learning Meets Security and Privacy Opportunities and Challenges. So Jinyuan right now is a postdoc in UIUC, and he will join Penn State as assistant professor in November or October this year. Yeah. And Jinyuan is got his PhD from Duke University under the supervision of Neil Gong. I consider Jinyuan as one of the rising stars, if not superstar, in the field of trustworthy machine learning, so has done many interesting works or impressive works in terms of the attacks and defense against machine learning models, especially his recent works on understanding the security privacy risks of self-supervised learning models. Anyway, so without further ado, Jinyuan, the floor is yours. Please go ahead.
Yeah, thanks for the introduction, Yang. It's my great pleasure to be here to share with you our research on machine learning, security, and privacy. Yeah, on one hand, machine learning provides more and more powerful tools for data analytics. For example, ChatGPT, right, is recently a very popular natural language processing tool, which can be used for various purposes, such as question answering. And machine learning is also enabling everyday products, such as smart home assistant, fingerprint authentication on mobile devices, robot assistant, and so on. On the other hand, security and privacy attacks increasingly involve data. For example, in the Facebook data privacy scandal, a company called Computationally tried to infer a large amount of Facebook users' private information via their publicly shared page likes. And the internet is also plagued by fake information, such as fake reviews and fake news. We have also witnessed one of the largest denial of service attacks caused by compromised IoT devices. So there are many interesting questions at the intersection of machine learning, security, and privacy. The first question is, how will machine learning impact security and privacy? And the second question is, how will security and privacy impact the deployment of machine learning? So let's first look at the first question. We focus on studying machine learning for security and privacy in social networking services, such as Facebook, YouTube, Twitter, and so on. On one hand, machine learning can be misused by attackers to perform automated large-scale inference attacks. For example, in the Facebook data privacy scandal, Cambridge Analytica leveraged machine learning to infer millions of Facebook users' private information via their public page likes. Such an attack is also known as inference attacks, and we actually predicted such inference attacks even before the data privacy scandal. On the other hand, machine learning can be used to enhance security and privacy. For example, we developed the first practical defense against inference attacks via adversarial machine learning techniques. We also developed a new graph-based method to detect fake accounts. Next, let's see more details about our work on defending against inference attacks. So what is exactly an inference attack? Let's use the Facebook data privacy scandal to introduce it. Suppose we have 5 Facebook users. These users have publicly disclosed their page likes. And 4 users also made their gender information public. However, user A thinks the gender information is private and thus does not disclose it. In the Facebook data privacy scandal, Cambridge Analytica first developed a Facebook app and use it to collect those public page likes and gender information. Then Cambridge Analytica tried to infer user A's gender using an approach as follows. First, Cambridge Analytica learned a machine learning classifiers using the public page likes and gender information of 4 users, B, C, D, and E. The classifier takes a user's public page likes as input and predicts the user's gender. Run Computationally applies the classifier to infer user A's gender using its public page likes. In this example, I assume the private attribute is gender. However, in the Facebook data privacy scandal, Computationally uses this approach to infer user's various private attributes, not just the gender. More generally, in social networking services, an attacker can collect users' various public data, such as page likes on Facebook, liked video on YouTube, rating scores on Google Play, and rating scores on IMDb. Inference attacks can use those public data to infer users' private attributes, such as gender, location, political view, and so on. To defend against the inference attacks, we need to understand why inference attacks succeed. The fundamental reason is that private attributes are statistically correlated with public data, and machine learning can capture such correlation from the public, capture such correlation to infer private attributes from the public data. Therefore, the key technique to defend against the inference attacks is to add noise to public data. However, a key challenge is what noise we should add to the public data. Like suppose the public data are rating scores. If we add a large amount of fake rating scores, then machine learning cannot infer private attributes from the public data anymore. But rating scores are often used for personalized recommendation services. If we add a large amount of fake rating scores, then recommendation performance is significantly influenced. Therefore, the key challenge is how to protect the user private attributes with a small amount of noise. In our work, we propose the first practical solution at regard. Our key observation is that an attacker uses classifier in inference attacks. But the classifiers classify adversarial examples incorrectly. So our idea is that we can attack the classifier while turning public data to adversarial examples. Adversarial examples are often viewed as offensive techniques that compromise the security of machine learning system. Our work shows that adversarial examples can also be used for privacy protection. Code and dataset is also publicly available. Next, we first formulate the problem of defending against inference attacks and then discuss how to solve the problem. Suppose we have a user and an attacker. The attacker has already trained a classifier, which takes the user public data such as page likes and rating scores as input, and predicts the user private attribute value. We can represent the user public data as a vector. For instance, for page likes, an entry of the vector is 1 if the user likes the corresponding page, and is 0 otherwise. For rating scores, an entry of the vector is the user rating scores given to a certain item, or 0 if the user did not rate the item. To defend against the inference attacks, we introduce a defender. The defender could be a software on the user client side. For example, the defender could be a browser extension. The defender adds noise to the user public data, and the attacker has access to the noisy public data. However, different users may have different preferences on what type of noise can be added to their public data. For example, suppose the public data are rating scores. Some users may prefer adding new rating scores, while other users may prefer, for example, modifying their existing rating scores. To incorporate such user preference, we introduce a noise policy, which specifies the type of noise that the defender can add. For instance, the noise policy could be modify exist, add new, or both. the defender adds noise to use the public data according to a noise policy to achieve two defense goals. The defense goal 1 is that attacker classifier should make incorrect predictions for the user private attribute value. The defense goal 2 is that the noise added to the user public data should be small to maintain the utility. However, achieving the defense goals faces several challenges. The first challenge for defense goal 1 is that the defender does not know the attack's classifier, as the attacker has many choices for its classifier. To address the challenge, the defender learns the classifier itself while leveraging user public data and public attributes, just like how an attacker could learn its classifier. Moreover, the defender adds noise to make its own classifier predict incorrectly. The second challenge for defense goal 1 is that the defender does not know user private attribute value. So the defender does not know whether its classifier makes incorrect predictions or not. To address the challenge, the defender adds random noise. Suppose the user public data vector is X, and those are the possible noise vectors. The defender randomly picks a noise vector R according to a certain probability distribution over possible noise vectors, and adds it to the user public data X. Since the defender adds random noise, the defender classifier prediction is also random. For instance, when the private attribute is gender, then the defender classifier prediction distribution may look like this, which means that the defender classifier predicts male and female with probability 0.4 and 0.6 respectively. With random noise, our defense goal 1 is refined to find a probability distribution over possible noise vectors, such that the defender classifier prediction distribution is close to a target probability distribution selected by the defender. For instance, the target probability distribution could be a uniform distribution over possible attribute values. Then the next question is, how to quantify the closeness between the two probability distributions? While there could be many metrics to quantify such closeness, we adopt K divergence between the target probability distribution and the defender classifier prediction distribution. We adopt K divergence because, as we will see soon, it makes our formulated optimization problem convex and have an elegant solution. The challenge for defense goal 2 is how to quantify magnitude of noise. To address the challenge, we use L0 norm of noise vector. We use L0 norm because it has intuitive interpretation. So as it measures how many entries of the user public data vector are modified. For instance, suppose the user public data are rating scores. L0 norm measures how many rating scores are modified or added by a defense. Next, we formally define the problem of defending against the inference attacks. Suppose we are given noise budget, for example, modifying or adding at most 3 rating scores on average. Our goal is to find a defense which is a probability distribution M over possible noise vector to minimize the K divergence. Formally, we can find the defense by solving the following optimization problem, where the objective is to achieve refine the defense goal 1, and the constraint is to achieve defense goal 2. This is the expected noise, and this is the noise budget. Next, let's discuss how to solve this optimization problem. It turns out that it's computationally intractable to solve the optimization problem exactly. Recall that our defense is a probability distribution over possible noise vectors. but the noise space is exponential to the dimensionality of public data X, which is often very large in practice. To address a challenge, we make a key observation that we can categorize noise space into M groups depending on the different classifier prediction, where M is the total number of possible attribute values. For instance, for first group of noise, if we add any of them to the user public data X, the defined classifier predicts attribute value 1. For second group of noise, if we add any of them to the user public data X, the defined classifier predicts attribute value 2. For last group of noise, if we add any of them to the user public data X, the defined classifier predicts attribute value M. Based on this observation, we propose a two-phase framework to approximately solve the optimization problem. In phase 1, we find a minimum noise as representative noise for each group. We find the minimum noise to reduce the utility loss. In phase 2, we simplify the defense to be a probability distribution over the M representative noise instead of all possible noise vectors. In other words, our defense randomly picks a representative noise with a certain probability and adds it to the user public data X. Next, let's see more details about phase 1 and phase 2. In phase 1, for each attribute value I, we aim to find a representative noise I, such that if we add noise I to the user public data X, the defined classifier predicts attribute value I. Formally, we can find the noise I while solving the following optimization problem, where the objective is to find a noise with minimum or real norm, and the constraint means that the defined classifier predicts attribute value I. It turns out that solving this optimization problem is equivalent to finding adversarial examples. So what are adversarial examples? Let me briefly introduce it. Recently, adversarial examples has attracted a lot of attention from both the security and the machine learning community. So suppose we have a panda image and an image classifier. The classifier can correctly predict the label of the image to be panda. An attacker can find some carefully crafted noise. And after adding the noise to the image, we get this new image. To human, this new image is still a panda. However, the image classifier predicts it to be monkey. This image with carefully crafted noise is called an adversarial example. By analogy, in our problem, we have public data X, and the defined classifier can correctly predict its label. That is, the defined classifier can correctly predict the user private attribute value. Our representative noise I is some carefully crafted noise, such that if we add noise I to the public data X, the classifier predicts attribute value I. This X plus I is called an adversarial example. Adversarial machine learning community has developed many methods to find adversarial examples. However, those methods are insufficient for our problem because they didn't consider the noise policy, which specifies the type of noise that the defined can. To bridge the gap, we propose a privacy-aware noise finding algorithm. So here I just give high-level ideas of our algorithm. Our algorithm iteratively finds the noise vector. In each iteration, our algorithm computes the gradients of the defined classifier's output with respect to each entry of the current noise public data vector, and then modify the entry that is allowed by noise policy, and that makes it most likely for the defined classifier to predict the attribute value I. After finding the M representative noise in phase 1, in phase 2, we simplify the defense to be a probability distribution over the M representative noise. Given such simplification, we can transform the original optimization problem into the following optimization problem, where P is the target probability distribution, and MI is probability of adding noise I to the user public data vector. This constraint means that its expected noise should be small. We can show that this optimization problem is convex, and thus many methods can be used to solve it. For example, we can use KKT conditions to solve it. After solving the optimization problem using KKT conditions, our solved defense is as follows, where Pi is target probability for attribute value I. Those are the KT parameters, and this is noise magnitude of noise I. Our solved defense shows that a defender picks the representative noise I with a probability that is proportional to the target probability Pi and is inversely related to the noise magnitude of noise I. Our solved defense is intuitive and interpretable. Next, let's see some empirical evaluation results. We use a rating score dataset, so from Google Play apps. And the private attribute is city-lived collected from Google+. This table summarizes our datasets. The total number of users is around 16,000, and the total number of apps is 10,000. Each user writes 23 apps on average, and the total number of cities is 25. We assume 90% of users disclose their public rating scores, and also they are city-lived. And the remaining 10% of users just disclose their rating scores, and the attacker try to infer their private city-lived. We will use this as a training dataset to train classifiers, and we use this as a testing dataset to evaluate classifiers. Since we do not know which classifier an attacker may use, we evaluate various attacks classifiers. So specifically, we consider two categories of the classifiers. For the first category, the attacker does not adapt the classifiers based on our defense. For the second category, the attacker adapts the classifier based on our defense. For the first category, we consider baseline classifier and various standard classifiers, such as logistic regression, random forest neural network. For the second category, since our defense leverage adversarial examples, attacker can use the classifiers that are robust against adversarial examples. For instance, we consider adversarial training, defensive distillation, and region-based classification. So this region-based classification is also known as some randomized motion, so it's very similar. So we also first to detect noise and ranking for private attributes. Here we leverage a low-rank approximation method to detect noise. This table shows the inference accuracy of different attacks classifiers without defense. So inference accuracy is the fraction of testing users whose city-lived are correctly predicted. This is a baseline classifier, which predicts a city that has the largest number of users in the training dataset for each testing user. This is the inference accuracy of standard classifiers, and this is the inference accuracy of the robust classifier. This is the first to detect noise and ranking for user private attributes. As we can see, machine learning enhances inference attacks. Machine learning classifiers are several times more accurate than the baseline classifier. In our defense, we need to specify noise policy, defender classifier, and target probability distribution. In this talk, I assume the noise policy is modified, which means we can modify user existing rating scores or add new rating scores. We assume the defined classifier is logistic regression, and the target probability distribution is a probability distribution of city lived in the training data. We also consider other settings, and the details can be found in our paper. This table shows that Idea is effective. So x-axis is the maximum number of rating scores that are modified or added by our defense for each user. Y-axis is the inference accuracy of different text classifiers. This is a baseline classifier, whose inference accuracy does not depend on our defense. As we can see, on average, modifying or adding 3 to 4 rating scores can reduce a classifier inference accuracy to the baseline classifiers. We're also comparing our Idea with existing defenses, including theoretic defense and differential privacy defense. This figure shows that Idea outperforms existing defenses. So x-axis is the number of rating scores that are modified or added by a defense on average, and y-axis is the inference accuracy, where the text classifier is the neural network. This is the curve of theoretic defense. This is the curve of differential privacy defense. This is the curve of Idea. This is the baseline classifier inference accuracy. As we can see, Idea achieved a better privacy-utility trade-off. For instance, in order to reduce the text classifier inference accuracy to the baseline classifiers, differential privacy defense need to modify or add more than 1,000 rating scores for each user on average. Theoretic defense need to modify or add around 30 to 40 rating scores, while our Idea only need to modify or add 3 to 4 rating scores. In summary, inference attacks are pervasive security and privacy threats, and Idea is the first practical defense against inference attacks. Adversarial examples are often viewed as offensive techniques. Our work shows that adversarial examples can also be used for privacy protection. Before I move to the next part, let's see whether there are any questions.
Hi, Jinyuan. I have a question. So regarding about the probability distribution, so how do you make sure that this kind of distribution is not close to 0? Because based on the KL divergence algorithm, if you have the distribution close to 0, it cannot be calculated, right?
Yes. Yeah, if you go back to our optimization problem. Let's see. Let me reshare the screen. Yeah, so when we solve this optimization problem, so essentially when this m equals p, so then KL divergence is real, right? So yes. Because this p is target probability distribution, so each entry usually in p is not real. So that means if we have this, we have a mi is equal real, then this KL divergence would be very large, right?
Yeah. Yes.
Yeah. So that's why it's not real.
Okay.
Yeah, I'm not sure whether this answers your question.
Yeah. Yes. Thank you.
Yeah.
All right. So we have another question from Manuel.
Yes. Hello.
Hi.
Thank you for the presentation. I think this can be called obfuscation, is that you are trying to hide the sensitive information from a user profile. Yes. My question is that in the technique you used, you said it's called modify alt, if I'm not wrong, sorry. Do you only modify the rating score of a user, or do you go to, for example, the cities that a user did not go to, or a movie the user did not watch, and you add a score, a fake score there?
Yes, I think, yeah, that's a good question. So we basically have, let's see, so.
The matrix.
Yeah,
Okay.
so here we have a noise policy.
Yeah.
So basically it specifies, so for example, the user can specify which type of noise they prefer. For example, like sometimes we modify their existing scores, or we can also add some new rating scores. So it's totally dependent on user preference.
Okay, and imagine if a user wants to modify a non-existing, wants to add a fake score to his profile, but we know it's fake. Imagine if the user will add so many fake ratings, then his profile is sort of fake. Would that have an impact on the utility of the system?
Yes, so you can see from this curve. So on average, we adding around 3 to 4 rating scores can reduce the text classifier inference accuracy to
but is
yeah. So
right.
Yeah, I didn't show the utility, but we indeed perform some experiments basically for recommender system. So
Yes.
basically those rating scores can be used for recommender system, right?
Yes, exactly.
Our results show that the impacts are pretty small.
Yeah.
So it can be found in our paper. Yeah.
Thank you.
Yeah. Thank you.
All right. So we have one more question from Ziyang Sha.
Yeah. Hello. Thanks for your talk. I'm just wondering if we want to protect the user's privacy instead of adding noise, can we have other solutions, or is there any other methods to protect this kind of privacy?
Yeah, that's a great question. So, I think in this kind of inference attacks, so it's based on user profile, right? So you can imagine if we do not add any noise to the user's public profile, then seems the attacker can somehow infer the private information, right? So that means we may need to add some noise, but to the user public data, but maybe the way to add noise could be different. Yeah, I think this is this answer your question?
Yeah, I got it. Thank you.
Yeah, thank you.
All right, so we have probably a bit two more questions for the first part of the talk, but okay. So the last one here for right now is Yiting Qu. Yeah.
Yeah, go ahead, Yiting.
Hi, thank you very much for your nice talk. And I believe this is a very practical work, could be very helpful in the industry. So my question is, since you mentioned that adding noise to users' information might hurt utility, for example, for some recommending systems, I was just wondering, have you tested the utility, well, at this work?
Yes. Yeah, so in our paper, we evaluate recommender system. So basically, we show how this rating, fake rating score impact the recommendation performance for each user. So here I didn't show the result in this slide, but it can be found in our paper. So we basically find that, for example, compared with many other defenses like gamma theoretical defense and different privacy defense, so the impact of the utility is pretty small. It's very, very small of our method.
Okay, I see. Thanks a lot.
Yeah, thank you. Yeah, thank you.
All right, so Jinyuan, please continue to the next part of the following part of the talk. Yeah.
Yeah, sure. Yeah. So let's move on to the next part. How will security and privacy impact the deployment of machine learning? So typically, a machine learning pipeline includes two phases: training phase and deployment phase. Suppose we have a machine learning algorithm, which takes the training data as input and train a machine learning model. The machine learning model can be used to make predictions for testing data. We study integrity and confidentiality of such machine learning pipeline. For integrity, we are interested in how this machine learning pipeline could be manipulated to make predictions as attack designs. For instance, an attacker can inject the fake data into the training data. An attacker can also compromise the training process or manipulate the model parameters. An attacker can also inject noise into its testing data, such that they are classified as attack designs. For confidentiality, we are interested in how model providers and model parameters could be compromised and how to protect them, and how users' private training and testing data could be compromised and how to protect them. Next, let's see more details about our work on how machine learning model parameters could be manipulated to make predictions as attack designs. We focus on self-supervised learning. A key challenge of the traditional supervised or transfer learning is that they require lots of labeled training data. Self-supervised learning is a pretty new technique to address the challenge. Self-supervised learning only requires lots of unlabeled data, such as unlabeled images or image text pairs, which we call pre-training dataset. A self-supervised learning pipeline includes two key components. In the first component, we use a pre-training dataset to pre-train an image encoder. So this image encoder is also known as foundation model. So given an image, this image encoder produces a future vector for it. In the second component, given some downstream tasks, such as traffic sign recognition, digit classification, and object classification, the image encoder can be used as a future extractor to build classifiers for those downstream tasks. Next, let's see more details about these two components. I will use a toy example to illustrate how SimCLR, a popular self-supervised learning algorithm, to pre-train image encoder. Suppose we have two unlabeled images. SimCLR first uses its data augmentation operation to create two augmented images for each image. Then SimCLR uses an image encoder to compute a future vector for each augmented image. The image encoder is updated such that if two augmented images are from the same image, their future vectors have logical similarity. And if two augmented images are from different images, their future vectors have small cosine similarity. Suppose we have some training images of a downstream task. Given an image encoder, we can use it to compute a future vector for each training image. Then we can use future vectors and labels of training images to train a classifier via standard supervised learning. Given a test image, we can use the image encoder to compute a future vector for it. Then we use a classifier to predict a label for the future vector. This predict label is viewed as the final prediction results for the given test image. In our work, we propose BadEncoder, the first backdoor attack to self-supervised learning. So what is backdoor attack? Roughly speaking, in backdoor attacks, an attacker can inject some backdoor behaviors into a machine learning model. And the backdoor behaviors can be activated when the input of the machine learning model contains a backdoor trigger. When the input is an image, the backdoor trigger may look like this. For instance, a white patch. Given backdoor triggers and a clean image encoder as input, our BadEncoder outputs an image encoder with backdoor behavior. We call it backdoored image encoder. When the backdoored image encoder is used to build classifiers for certain downstream tasks, those classifiers simultaneously inherit backdoor behaviors. For instance, when the backdoor image encoder is used to build a classifier for the traffic sign recognition task, the classifier can correctly predict the stop sign image. But if a white patch is added, the classifier predicts the speed limit of 6 miles per hour as a tag device. The behavior of the classifiers for the digit classification and object classification are similar. Our BadEncoder shows that a backdoor image encoder can lead to a single point of failure of the entire AI ecosystem. Next, let's discuss the threat model. We consider two possible attacks. First, the attacker can be an untrusted model provider. The model provider pre-train an image encoder and craft a backdoor image encoder. The backdoor image encoder is shared with customers. The attacker could also be a malicious third party. For instance, the attacker can first download an image encoder from the internet and then craft a backdoor image encoder and republish the backdoor image encoder to share it with customers. To perform the attacker first select a downstream task and a class, which we call target downstream task and target class. For instance, they could be traffic sign recognition and speed limit of 6 miles per hour. In our BadEncoder, an attacker can select multiple target downstream tasks and multiple target classes. For simplicity reason, I will focus on a single one in the rest of the talk. An attacker aims to craft a backdoor image encoder to achieve two goals. The first goal is the effectiveness goal, which means that backdoor attacks should be effective. The second goal is the utility goal, which means we should not sacrifice the utility of image encoder. To reach the attack goal, we assume the attacker has some unlabeled images, which we call tag dataset. For instance, when the attacker is an untrusted model provider, the attacker can use its pre-training dataset as a tag dataset. When the attacker is a malicious third party, the attacker can use some publicly available dataset as a tag dataset. We also assume attacker has image in target class, which we call reference image. For instance, when the target class is speed limit of 6 miles per hour, the reference image could be an image of 6 miles per hour, as shown in this figure. The key idea of BadEncoder is that we formulate BadEncoder as an optimization problem. We use the effectiveness loss to quantify effectiveness goal, and use the utility loss to quantify utility goal. Then we minimize a weighted sum of the two losses to craft a backdoor image encoder from a clean image encoder. However, achieve those goals faces several challenges. The challenge of quantifying effectiveness goal is that the training process of the classifiers for the target downstream task maintains the integrity and confidentiality, so the attacker cannot exploit such process to craft a backdoor image encoder. To address the challenge, we make a backdoor image encoder produce similar future vectors for reference image and any image embedded with a backdoor trigger. Therefore, a classifier built upon the backdoor image encoder is very likely to predict the same label for the reference image and image embedded with the backdoor trigger. When the reference image is correctly predicted as a target class, then the image embedded with backdoor trigger is very likely to be predicted as a target class. Formally, we define the following loss. Here, DA is an attack dataset, and X is an image in the attack dataset. S is cosine similarity. F prime is backdoor image encoder. E is backdoor trigger, and X plus E is the image embedded with backdoor trigger. XI is reference image. This is normalization parameter. which is the number of images in the attack dataset. However, L0 alone is insufficient because the reference image may not be predicted as a target class. Therefore, we also make a backdoor image encoder and a clean image encoder produce similar feature vectors for reference image. Formally, we define the following laws. So here S is the cosine similarity, F prime is a backdoor image encoder, F is a clean image encoder, XI is reference image. Our final loss to quantify effectiveness score is as follows. Here lambda is a hyperparameter. The challenge of quantifying utility score is that the attacker does not know which downstream task the backdoor image encoder will be used for. So it's very challenging to directly quantify utility score. To address the challenge, we quantify utility score using the outputs of the backdoor image encoder. In particular, we make a backdoor image encoder and a clean image encoder produce similar feature vectors for images in the attack dataset. Formally, we define the following laws. Here DA is the attack dataset and X is an image in the attack dataset. S is the cosine similarity. F prime is the backdoor image encoder. F is a clean image encoder. Our final optimization problem is as follows, where lambda 1 and lambda 2 are two hyperparameters. We can minimize this loss to craft a backdoor image encoder from a clean image encoder. This optimization problem can be solved using gradient descent. Next, let's see some evaluation results. We use SAV10 as a pre-training dataset and use SimCLR, a popular self-supervised learning algorithm, to pre-training image encoders on the pre-training dataset. We consider GTSRB, SVHN, STL10 as downstream tasks, which respectively represent traffic sign recognition, digit classification, and object classification. Each downstream task has a training dataset and a testing dataset. We use a training dataset to train classifiers and use a testing dataset to test the classifier. We use a fully connected neural network as a classifier. In our attack, we need to specify attack dataset, reference image, and hyperparameter. In this talk, we assume the pre-trained dataset is an attack dataset, and we collect images from the internet as a reference image, and set lambda 1 and lambda 2 to be 1. We also consider other settings, and those details can be found in the paper. We use a attack success rate to evaluate the effectiveness of our BadEncoder. Given some clean test images, we can add a backdoor trigger to each of them. Then we use a classifier that is built upon backdoor image encoder to predict label for each image with backdoor trigger. Attack success rate is defined as a fraction of images with backdoor trigger that are predicted as a target class. So in this example, the target class is a speed limit of 6 miles per hour. This table shows that BadEncoder is effective. The first column is a target downstream task selected by the attacker when crafting a backdoor image encoder. As we can see, BadEncoder can achieve very high attack success rate, which means that BadEncoder is effective. We use clean accuracy and backdoor accuracy to evaluate the utility of clean image encoder and backdoor image encoder. Given some clean test images, we can use a classifier that is built upon clean image encoder to predict label for each image. Clean accuracy is defined as a fraction of images that are correctly predicted. Similarly, we can use a classifier that is built upon backdoor image encoder to predict label for each image. Backdoor accuracy is defined as a fraction of images that are correctly predicted. This table shows that BadEncoder maintains the utility. So first column is target downstream task when selected by the attacker when crafting a backdoor image encode. The second column is downstream task that we evaluate the utility of clean image encoder and backdoor image encoder. As we can see, backdoor accuracy is similar to clean accuracy, which means BadEncoder maintains the utility. We also evaluate BadEncoder using a real-world case study. We apply BadEncoder to OpenAI's image encoder, so which is pre-trained on 400 mini image text pairs collected from the internet. This OpenAI is a research company, and this pre-training dataset is not publicly available. So we use a subset of the ImageNet dataset as a attack dataset. Similarly, we collect images from the internet as a reference image and set lambda 1 and lambda 2 to be 1. This table shows our experiment results. So we have two observations. First, attack success rate is very high, which means that BadEncoder is effective. Second, backdoor accuracy is similar to clean accuracy, which means BadEncoder maintains utility. We also generalize existing defenses designed for classifiers to defend against our BadEncoder. We consider empirical defense and proof defense. For empirical defense, we consider neutral cleans and MTD, which are two state-of-the-art methods to detect whether a classifier is backdoored or not. For proof defense, we consider PageGuard, which can build a provably robust classifier. So here I just show the conclusion from our experiment results. We find that neutral cleans cannot detect backdoor image encode, and the detection accuracy of MTD is close to random guessing. PageGuard provides insufficient robustness guarantee. In summary, so we propose the first backdoor attack to self-supervised learning, and we find that insecure encoders lead to a single point of failure of the entire AI ecosystem. Existing defenses are insufficient, so we need a secure self-supervised learning algorithm. Finally, I would like to thank my advisor, Neil, and my collaborator, the UP. Thank you. Let's see whether there are any questions.
All right, I think that's the end of the talk. So I will stop recording and